CS402 on Wednesday, July 2nd, 2014.
Night. And again, final reminder, if you have code from previous semester, don't copy from it, get rid of it. Grading guidelines, the only way we will grade, and make sure you verify your kernel submission. Okay, follow the procedure. The midterm exam is next Monday during class time, so it's an entire an hour and 15 minutes. It's going to be in SGM 101, so don't come to this room, go directly to SGM 101. And all the information on the class webpage, please take a look at it. And the final exam will have no overlap in coverage, from the midterm exam. So of course the final depends on, some of the stuff at the beginning of the, the book chapters. But, the sort of the coverage is going to come from the rest of the semester. Okay, and again, the midterm cover everything from the beginning of the semester to the end of the last lecture, except if things are in chapter 5 and 6, then they are not covered. Okay, anything that's in chapter 1 through 4 are covered. And again, final reminder that the best answer to questions in the exam, is the one on the lecture slides. So when you study the lecture slides, and if you have things that you don't agree with me, please send me email. Okay, and then if it turns out that I was wrong, we can fix the slides, and I will make an announcement over the class Google group. All right. Okay, and kernel 1, I guess I've been sending out email. Some of the emails sort of refer to this picture, okay? And this picture turns out to be a very important picture in kernel 1, right? I mean, you need to be able to answer a question such as, where are all the threads, right? Okay, so this is an important question. Anytime you're in the kernel, no matter who's executing, you should be able to answer this question, where are all the threads? Okay, if you run a favor test, looks like things is going crazy. Where is every thread? Do you know where every thread is? Right, you should know, right? Okay, if you understand what the kernel is supposed to be doing, given that we have a non-preemptive kernel, okay, there's only one guy running as a current thread. All the other threads are waiting in some queue, right? Okay, where is the pageout daemon? Where is the idle process? Okay, you should be able to answer all these questions, right? Okay, and of course you need to know what are all your possible queues, right? All these things belong to queues. What are all the queues in your in your system? Okay, in the beginning when you get into init proc run, okay, how many you have 3 threads, right? Where are they? What are the queues? And all these kind of stuff. When you run favor tests, more queues get created. Okay, so you need to be able to answer this question, and you need to be able to say, well, how does this thread get on that queue? Okay, how? It's not a sort of a hypothetical situation. Exactly which function, which line of code get that thread onto that queue, and also whose responsibility is it to make this queue runnable again? Right? Once you're sleeping on the queue, somebody has to move. I mean, the thread itself cannot move itself away from that queue onto the run queue. So there must be somebody else. Who is this somebody else that's going to move that thread from that queue onto the run queue? Okay, once you get on the run queue, you have to wait your turn, and eventually you become the current thread. Okay, so by when you finish kernel 1, you should have these very, very clear picture in your head how all the threads and all the processes interact, right? And we have one thread per process, so thread equal to process in this case. but how all these, kernel threads and processes works together, to switch from one another. All right, so non-preemptive kernel should make the picture, should make this picture really easy to draw, and you should be able to do that. All right, and if you're still not clear about this, send me an email. And when we talk about, like I have code in my Faber test, this is happening, that is happening. Well, draw this picture to figure out where every thread should be, and then figure out why is a particular thread not in where it's supposed to be. Okay, and there is there's also a data structure where in the kernel that keeps track of all the threads. You should be able to walk down that thread. There's a list that keeps track of all the thread that has been created. You should be able to walk down that list and then examine that data structure and find out where every thread is where they're supposed to be. All right? Okay, so important picture. All right, my hope is to finish chapter 6, or at least the first set of slides, introduce you system file system to you. And hopefully next Wednesday,
the time is 0 o'clock.
Start talking about chapter 7. All right, and then when we're done with chapter 7, we're going to come back and finish chapter 6, because chapter 6 has other very important material. They're not related to your kernel 3, so that's why I'm going to talk about them after we're done with chapter 7. Okay. All right. So last time we talked about system file system. What is the basic layout of the of the disk partition? So there's the boot block, there's a super block, there is the the array of inode, right over here. Although it says list, it's just an array of inodes, and then over here there's an array of just data blocks, and every block has a block number. Okay, so they're just an index, that kind of a block number. And every inode also have an inode number, and again, it's just an inode index, okay, into this, this table. Okay, and inode looks like this, right? We explained all these fields last time, and then we're starting to look at what a disk map look like. And disk map is fixed size. It's an array of 13 pointers, okay? And some of these pointers are, so there are 13 pointers, but there are 4 different kinds. Okay, so last time I mentioned that the first, first 10 are direct pointers, and then this one is an indirect pointer. This one is a double indirect. This one is a triple indirect. Okay, so let's see what that means. All right, so if you have a file that's very small, okay, all right. So the assumption we're going to make is that every block it's of size 1 kilobyte. Okay, so typically. I think we talk about that a memory block is 4 kilobytes, so the disk block in this case is smaller than, so smaller than the memory block. Okay, I guess in the good old days of when system file system started, a block size is half a kilobyte, and later on they changed it into 1 kilobyte. Okay, so over here we're going to assume 1 kilobyte because it's really easy to talk about, right? So if you have a file that's less than 1 kilobytes long, then what happens is that it's only going to use up to the first 10 disk pointers. Okay, if you create a file that's only 1 byte long, okay, what happens is that all these pointers will be null, okay, and the first pointer will point to the disk block that has that 1 byte in it. Okay, so the total waste of space, right? This file is only 1 byte long. Okay, we're going to allocate 1 kilobytes to hold 1 byte of data. All right, but there's no other choice because that's how the system file system work. You allocate, the minimum allocation size is 1 kilobyte. Okay, if you have a file that's, 900 bytes long, right, then you're going to use, 9 blocks. If it's, a little less than, 10 kilobytes long, then it's going to use up 10 blocks. Okay, and now if you continue to append to the disk, now you're going to get, the file's going to get bigger. Okay, if you go beyond the first 10 pointers, so the first 10 pointers are direct pointers. Okay, they reference directly to a disk block. Okay, and each one of them contain an integer, right? I tell you which disk block it points to. Okay, if your file gets a little bigger, then what happens is that you're going to need the next pointer. The next pointer is an indirect block, okay, which means that the disk block that mentioned in over here contains another disk block that has 256 pointers, right? So this disk block is 1 kilobytes long, right? And each pointer to the disk is just an integer, so it's 4 bytes long. And you can actually put 256 of these bytes, 256 of these pointers inside this block. Okay, so where is this block sitting? This block is also sit in the blue region that we talked about before. Right? That block is also here. Okay, so these indirect block and the direct data block, they're all sitting over here. And the inodes, right, are the one that sit in the I list. Okay, sorry. The inode, that's the one sitting in the I list, and the disk map is just an array of 13 pointers. All right, so I hope that this picture is clear. Okay, and then each one of this guy is a pointer that's just like, the pointers 1 through 10, so they point to a disk block directly. They contain an integer that tell you which block they point to. All right. Okay. So what if so you have 256 of 1 kilobytes block. So this points to a collection of 256 kilobytes. Each one is 1K, and there are 10 of them, so that's 10 kilobytes. Okay. So together, if you use the first 11 pointer, your file can be as big as 10 kilobytes plus 256 kilobytes. Okay. If your file needs to get a little bigger, then you have to use the next pointer. Okay, the next pointer is double indirect. Okay, that means that they point to a block of 256 pointer, and each one of them point to 256 of the green ones. Okay, so 256 times 256, you're going to end up with 64 megabytes. So if you follow this pointer, these blocks all together can hold 64 megabytes of data. All right, and this one hosts 256K. These guys host 10K. So if your file is within this limit, it will only use the first 12 pointer. Okay, what if your file is bigger than 64 megabytes? Then you have to use the last pointer, and the last pointer is triple indirect. Okay, so this one points to, over here I color it yellow. Okay, of course they don't have colors. So this one points to 256 of these guys, and each one of these point to 256 of these guys, and each one of these point to 256 of these guys. Okay, so if you multiply them all out, this entire thing over here, going through the 13th pointer, that will give you 16 gigabyte. All right, so your largest file, that you can have for the system file system is a file of this many bytes. Okay, so that. That's just a single file. All right, so so even though that is the maximum possible file size, system file system artificially limit the largest size of a file is to be 2 gigabytes. All right, so this is so this is how you go from the inode go from the inode to look for all the disk block that belong to this file. Okay, so. We talk about the system file system. We sort of have the assumption that when you try to access the file system, mostly you're doing sequential access. Okay, so what does that mean on this picture when you do sequential access? That means that you're going to open the file, you're going to read this block, and then you're going to read this block, right? You're going to read this block first, followed by this block, and then followed by this block. When you're done with this block, the next block you're going to read is this block, right? Okay, and then it's this block, etc., right? And then when you're done with all these blocks, the next block you read is going to be this block. Okay, so is this efficient to to do sequential reads? It's not so bad. Okay, so the idea for the file system is that disk is a very slow device. Okay, so if you want to optimize the performance of the disk, you got to try to minimize the number of reads to the disk. Okay, and every time when you read to the disk, you can read, 1 page. Okay, so in this case, if you want to get to this block, what do you have to do? Right, you have to go to the system file system, that entire file structure, go find the inode, right? Once you find the inode, then you know where the disk map is, then you access the first pointer that will get you this one. Okay, so once you find the inode, then it's 1 disk read to get this data. All right, so it's not so bad, right? Okay, and sequential, once you read in the inode, then if you go to the next one, it's another disk read. So every disk block will cost you 1 disk read. So it's not so bad. What about random access? If you have a large file, I want to go to byte number 725.000.000. I want to go to this byte. All right, I call lseek. I want to seek to this position. Right? Remember when you call lseek, all it does is change the cursor position in the system file table to this number. Okay, and then when I say read, what it will do is that it will go through this structure, try to find out where this is. Okay, how long would it take you to find this particular block? Right, once you have this data structure, or you can just do some arithmetic, right? Find out that in order for you to find this byte, you have to go to the 13th pointer, right? Okay, and then you do triple indirect. You got to read one disk block, and then another disk block. Okay, and then this one you can do some arithmetic. Will tell you to read which is the next disk block, and then finally that would lead you to the disk block containing that byte of data. Okay, so if you have the I node, you just have to do 1, 2, 3, 4, and 4 reads will get you to this block. Okay, so in a file that's 2 gigabytes long, it will take you four reads to get to this block. Is that bad? I mean, it's constant time, right? Okay, if you want to read any disk block, okay, it will cost you at most 4 disk reads. Okay, so this kind of stuff is sort of, when you design a file system, you got to sort of keep that in mind. You want to minimize the number of disk reads. Okay, because disk reads, we're going to see very soon why, disk reads are so slow. That's because of the way the disk is organized. All right. Okay, so so that's the basic structure of what an inode is and what the disk map in an inode, how are all the disk block organized. In the super block, I already mentioned that it keeps track of free lists. Okay, so system file free, the free list look like the following. Okay, the super block contains the address of up to 100 free disk blocks. Okay, if this is the super blocks, inside over here, there's an array of 100, disk pointers. Okay, again, 100 integers. Okay, the first 99 of them point directly to the blocks that are free. Okay, so this one, if you follow the pointer, it will tell you a block that's free. So why do you need that? Okay, because the file system, all it does is, allocating space to put data in for files and also, free up space, right? So one thing that you do very, very often in the file system is somebody wants to create a file. Well, they need a free block. You say, well, here's a free block. Okay, so this operation needs to be done very, very quickly. Okay, you need to tell, this application to say, well, here's your free block. Okay, so the first 99 point directly into free blocks. The next one, the last one, the 100th one, that one point to, so by the way, these things, I color them blue, right, because they were in the data region. Okay, this last guy, they point to another disk block. Okay, and this disk block also contain 100 entries that looks just like this one. Okay, so if you follow this pointer, it will point to another block that in the blue region. Okay, the first 100 pointers over here, or the first 99 of them, again, points directly to a free block. And the last one is like a linked list, point to another one that has 100 pointers in them. And then the 100 of them, again, points to the 100 of them. Okay, so the idea over here is that if you start from the super block, you should be able to find all your free blocks. Okay, all the free blocks can be traversed starting with the super block, right? Here's 99 of them, and then here's the next 99, here's the next 99, here's the next 99. All right, and these blocks, I mean, they are used by the file system, okay? But these blocks, supposedly they're also free, right? Because they are really not allocated to any of the files, okay? But just like when we look at the memory allocation slides, if you have free, memory blocks, well, internally you can use them for any kind of pointers and stuff like that. Okay, and that's exactly what happens over here. Here's a free block, but, the file system is using this block to point to, other free blocks. All right, or in the tree data structure, right, you have the first free block, you have 199 pointers over here. The next guy points to another node that has 99 pointers, et cetera, right? So it's a linked list. Okay, it's really not a tree, but just a linear linked list. All right, so knowing that it sort of looks like this, okay, what happened if you start allocating free blocks? Okay, somebody call one of the routine in the file system to say, I need a free block. The file system says, here it is, right? So then knock out the first one and return this one to the application. Well, it doesn't have to be the application. It could also be the kernel need a disk block. Okay, so we allocate this one, return the disk number, this one, to whoever that needs it. And now this one, you will point it to null, right? To say it's no longer free. Okay, and then somebody asks for another one, you allocate this one, you allocate this one. Eventually, you're going to allocate everything. All the 99 pointers over here are allocated. Okay, next time somebody say, I want a new block, what do? All right, so what you do is you go to the last pointer, right? This one points to this place. What you do is that you do a mem copy, right? You read this block into memory, and you copy this entire 100 pointer right over here. Okay, if you copy this entire 100 pointers over here, then how do you interpret this data structure? Okay, then this pointer now points to wherever this guy's pointing to, right? So pointer 99 over here will point to a free block. Pointer 98 will point to a free block all the way, And what about the 0th pointer? The 0th pointer will point to wherever this guy was pointing to, right? So the 0th pointer will point to this page. Okay, so again, this is like a linked list. You remove the head of the linked list, okay, and now you make the second guy on the linked list to be the new head of the linked list. Okay, and the head of the linked list is always sits in the super block. Does that make sense? Okay, so this is how you allocate blocks from the file system. Okay, what about when you try to free something? Okay, when you try to free something, okay, so let's say that the first some of these pointers are available. Okay, when you try to free a block, all you need to do is to use the last pointer over there to point to that free block. Right? Somebody has this block, say, this block is no longer in use. I want to return it back to the file system. So you allocate the next entry, and then you point to this one. All right, so that's how you return a block to the free list. Okay, and then eventually this list is going to be completely full, right? Okay, if all the 100 pointers are used over here, somebody's returning to a free block, what do? Okay, so what you do is that you take all the 100 pointers over here, you copy over here, into this block. Okay, when you copy the content of this 100 pointer to here, what do you end up? Right? If this guy is pointing right here, now this guy will point right here. If the second entry was pointing to this block, now the second entry will point to this block. If the 0th entry pointed to this one, now this guy will point to this one, right? Okay, that's what I mean when you copy the entire content into this free block. Okay, so you free this entire thing up, right? You set the pointer 99 through 1 to be the null pointer, and then you have the 0th pointer point to this block. Okay, is your free list intact again? Right, now it looks like the free list, right? Because, the head of the free list in the super block, all these pointers are null, right? So this one points to, the next blocks that has a list of free blocks. Okay, so again, your free list, going back to the sort of the consistent data structure, and now you can find all the free blocks starting from the super block. All right, so this is how you free a block, to the file system. All right, let's look at, right, so basically that was it. For the free list, the maintenance is very simple, right? You allocate from it, and then you deallocate, returning a block to it. Okay. What about the inode? Okay, so the inode inside the ilist, okay, it's just an array of inodes, right? So I guess one field that were left out in the data structure is whether the inode was allocated or not. Okay, if it's allocated, that means that what does it mean when an inode is allocated? Right? Inode means a file, right? So if a file is allocated, that means that you can find this inode in the file hierarchy, in the file system hierarchy. Okay, file system hierarchy meaning start from the root, it's a big tree, right? If you can reach a particular, inode from that tree, well, that is part of the file system. Okay, if an inode is not, in the file hierarchy, that means that the inode doesn't belong to a file. Okay, so over here, we're going to have one extra field over here to say that whether this inode is allocated or not. Okay, if it's 0, that means that it's not allocated. That means the inode is free. Okay, if it's equal to 1, then that means that that inode is actually being used. Okay, so in the super block, we also keep track of some of the free inodes. Okay, and the reason we want to sort of put them in the super block is because, again, we need to get to these things very quickly. Okay, and one way is to put them into the, into the super block so that they are quote unquote cached. Okay, so over here, this is called the inode cache. Okay, there's some entries over here. I don't know how many exactly in the system file system. Maybe also 100 of them. Okay, you're gonna have 100 locations that points to where are the first 100 free inodes. It doesn't have to be the first. Just any free inodes will be fine. Because whenever you need to create a file, okay, you need a new inode. Right? So therefore, we're going to have entries over here. Anytime anybody wants to create a file, well, you say, well, here, here's one for you. Okay? So in this example, inode number 4 is free. Right over here, 4 is free. Inode number 12 is free. 6 is free. 11 is free. 13 is free. Right, etc. I mean, there are other free ones. I didn't write it in them. Okay, so some of the entries over here in the IList, in the beginning, when you have nothing in your system, right? Everything is free. Once you start installing, file system, once you start install files in, /bin/user bin, then you're going to use up a lot of entries. So you can see that in the IList at the beginning, most of the entries are being used, for the files, for the file system. Okay, so towards the end, there's a lot of free inodes. Okay, so the inodes are cached over here. Okay, so if somebody wants to create a file, okay, it needs an inode. So you're going to allocate out of these inodes in the superblock. Okay, so you're going to find the first one in the superblock that's free, and you say, well, here's a free inode. Right, the first one we find is number 4. Now number 4, we're going to say it's being used, and then that file can use this inode. All right, next time somebody asks for another one, we're going to go to the next one, number 12. Number 12 now it's being used, and then that file can use up this one, etc. Okay, what if you use up all the entries over here? Okay, in system file system, if you use up all the entries over here, what the file system have to do is to scan the IList, okay, to look for free ones. Okay, if there's 100 entries over here, it will come and scan the entry and the IList, look for 100 entries and cache them over here. Okay, so cache them meaning that you just have the pointer point to these blocks where the inodes are free. Okay, so if this, how long this IList? It must have, hundreds of thousands of entries in them, right? So if you need to scan them, the way you scan them is that you scan from the bottom, okay, and then go until you find 100 entries. If at the beginning of the disk all the entries are being used, then you are sort of wasting your time going through those entries. Okay, so another thing that you have to do is to find a good place to start looking for these free inodes. Okay, so if the inodes is huge, right, the bottom part is all used. Starting over here, there's going to be free ones, scattered all over the place. Okay, so what you would do is that you will store, I guess, kind of like a low watermark to say where is the lowest inode number that are free, that is free. Okay, so this picture, this one is the lowest inode that's free. Okay, so therefore, I'm also going to keep track of that in the super block of the low watermark. Okay, so this way, what I can do is that, again, I can use, some arithmetics to tell me where is the first place to look on the disk for this particular information. Okay, then I will find the first one, and from this point on, I will do a sequential scan of the inodes to find, 100 free ones. All right, and anytime when I try to free an inode, okay, I delete a file, right? When you delete a file, the file is gone, so you don't need an inode anymore. At that point, the inode is going to be returned to the file system. Okay, so what you can do is that you will, so let's say that this is the one that you return. You're returning right here. Okay, this one becomes free. Okay, so therefore you have to go over here and mark that one free. Okay, if it turns out that this one is actually below the low water mark, you have to reset your low water mark to be right here, right? So now this becomes a low water mark. Okay, so you have to sort of, in the file system, you have to keep track of where the low water mark is. Anytime somebody returns an inode, you can compare against it. If it's lower, you reset the low water mark. Okay, so next time when you run out of inode, you can go over there and start scanning. All right, when you return the inode, what you would do is that you will add an entry back into the super block for the free inode. Okay, so whatever you update over here, you also need to add that entries right here. Okay, eventually when your inode cache is full, right? So let's say that 100 entries over here, you're deleting a lot of files, and pretty soon this entire thing is full. What do you do when this entire thing is full? Right? How about nothing? Okay, so over here, if all the entries are full, right? I mean, these are cached free inodes. So if you have already 100 in the cache, so you don't have to touch it anymore. Okay, so you can just free up inodes over here, adjusting the low watermark, but over here you don't have to do anything. All right, so this is basically how you operate the inode list. All right, so I guess so when you create a file, what has to happen, right? When you create a file, you need free blocks for the data, right? Every file has to have at least we do have file of 0 size, okay? But you can also allocate 1 block for that file because the empty file doesn't really doesn't really exist very often. So you need to allocate a free block for data, right? It's one of the blue blocks over there, okay? And then when you get a free block, you need to go to the free list in order to get a free block, okay? So therefore, you need to update the free list, okay? And then since it's the new file you created, you need also the new inode, so you get a new free inode, okay? And then you update the ilist and maybe the inode cache. All right, so this is the other operation that you have to do. Okay, when you delete a file, okay, then all the blocks, right, starting from so if you're deleting a file, you know where the inode is, okay, and you go to the inode, you go to the disk map, you look at all those blocks, and you have to free all those disk blocks, okay, whether they're direct or indirect, you got to free all of them, right? So you're going to free all these disk blocks, add them all back to the free list, make all the adjustment of the free list that you need. In the end, you got to have a valid, free list. Okay, and then you mark the inode free in the ilist, and you may have to update the inode cache. All right. Okay, so that's sort of the basic structure of the system file system. All right, it's very simple, and it's good for sequential access, and even it's good for random access. All right. So now we're going to sort of talk about what the disk look like, and then we're going to say, well, why is system file system so slow? And then we're going to talk about what kind of an improvement that were made to the system file system. Okay, so first we'll look at what a disk look like. Okay, so this is what a hard drive look like. Okay, so over here, the hard drives are made out of these platters. Okay. Every platter has 2 surfaces, one on top, one on bottom, and both surfaces can store data. Okay, and the data are stored in concentric circles. Okay, so there are many circles. I mean, the disks are circular. There are many of these circles, and they are called tracks. Okay, so on one surface there are I don't know, hundreds of thousands of tracks on them. Okay, and every track is divided into little segments that are called sectors. So this one, here is one track is divided into, again, thousands of tens of thousands of sectors. Okay? So that's how, so the data are stored within the sectors, and the smallest addressable unit on the disk is a sector. So you cannot say, I want to read a byte from the disk, or write to a byte on the disk. You can only read and write sectors. Okay? So how do you get to a particular sector? Okay? In this case, there are 8 surfaces. The example, there are 4 platters, so there are 8 surfaces. So you have to say which surface that you're looking for. And on each surface, you want to say which track you want. And on that track, you have to say which sector that you want. Okay, so in order for you to get to a sector of data, you have to say what is the surface number, what is the track number, and what is the sector number. Okay, so 3 things to get to a sector. All right. So the way that you read data or write data, on a particular a sector is the following. The disk has this hardware. So the way that the disk work, right? They are magnetic material. So what you need to do is that in order for you to store data, you need to magnetize these bits inside the sector. And if you want to read them, you have to sense these magnetized bits. Okay, so there are these magnets, and the magnets are sitting on this black thing right here. Okay, so these are called disk head. Okay, all right. So if you have 8 surfaces, you have to have 8 disk heads. One sits here, one sits on the other side, one sits on the second platter, one sits on the other side. So every surface has a head. Okay, so the other way to sort of tell us which sector you want is you specify a head number followed by a track number followed by a sector number. All right, so this head, what you will do is that, in order for you to read a particular data, what you need to do is that you need to, you need to wait for the, for the sector to come under the head. Okay, so what happens is that the way these heads work is that they're sitting on these things called the disk arms, and the disk arms is fixed. They cannot move. Okay, so you have to think of this arm that comes out. So it's almost like a toothbrush. The arm is here, and then you have a disk head right here. Okay, and this is where the data has to be before you can read or write that particular sector. Okay, and this cannot be moved. Okay, so what you need to do is that you need to, although the disk head can move in the radial direction, okay, here is the, I guess we're fixing on the left side. Okay, so this side is fixed. This one can move in and out, okay, in a radial direction. Okay, so if you need to read, let's say if you need to read this sector, what you need to do is that you need to tell the disk head to move to that track. Okay, maybe right now the disk head is at the wrong place. You need to have it go to the right track, and that particular operation is called seek. Okay, you need to ask the disk head to seek to the right track. Okay, and when you're at the right track, you have to wait. Right? So this is spinning. Okay, so you have to wait for that sector to come under the disk head. Okay, so over here, this guy's spinning. Let's say spinning in this direction. Okay, you have to wait until this guy go right underneath the head. At that point, you will turn on the reading mechanism. Okay, so that the magnetized bits can be read by the disk head and then get turned into electricity, and then the electricity are sent through the disk arm. This guy connects to the disk controller, okay, and this guy go over the bus, and then it will, here's memory. Okay, so these data will go on to the disk controller. The disk controller has a buffer. Okay, so buffer are just memory, memory chips. Okay, so these data will go onto the memory chips. When they all stay in the memory chip, and that's when, when all the sectors get into the memory chip, that's when the disk controller will issue a DMA to transfer the data into main memory. Okay, and that's the only way to get data off the disk. Okay, so you got to, so with all these heads, actually all the 8 heads, they move at the same time. Okay, so you can only read from one surface at a time. I don't know if there are disks out there that can, have independently moving heads. I think those disks are really expensive. Okay, so the typical disk, they will move all the heads at the same time, so you can only read from one surface and one track, and I guess all the sector on the track, supposedly you can actually read them. Okay, so if your disk head is sitting over here, right, if you want to read the entire track onto the disk controller, is that possible? I mean, it is possible as long as you have enough memory on the disk controller. Okay, so you can buy a more expensive disk controller. So when the head is sitting over here, it can actually read the entire track of data and put them into the to the buffer over here. Okay, and then it will transfer that into main memory. Okay, so the reason that this is really slow, okay, is because so in order for you to read data, right? What are the what do you have to wait? Okay, so let's say that you tell the disk controller, right? Here's your device driver. Okay, your device driver is executing the CPU. Okay, what it will do is that it will tell that this controller says, give me, that particular sector sitting at head number 3, track number 52, and then sector number 187. Okay, so what's going to happen right now is that the disk controller know where the head is. Okay, so it will perform a seek operation to seek to the right track. Okay, so it's going to go to the right track, and then it's going to, so that's called the seek time. Okay, so let's say that this is called transfer. Okay, you want to transfer a block, so transfer time is going to be equal to seek time. Okay, so seek time is for the disk head to move to the right track. Okay, and then plus something called rotational latency. Okay, rotational latency is for the sector to come under the disk head. Okay, and then once it goes under the disk head, then these bits is going to go directly into the buffer. Okay, then plus this is called transfer time. Actually, this transfer time equal to transfer time sounds like recursive definition. So this is the read time, I guess, or read time. Okay, and then followed by transfer time. All right, so to read a sector of disk, okay, you got to wait for the seek time, and then wait for rotational latency, and then finally, do the transfer time. Okay, so when you do the transfer time, actually, you have 8 heads. If you switch any one of the heads on and off, that's electronic. That doesn't take any time. Okay, the seek time and the rotational latency, these are done by mechanical devices, so therefore they are really, really slow. Okay, so when you need to perform this kind of operation, it can take you, milliseconds. Okay, the data transfer time, that one is actually really quick. Okay, because your disk is actually spinning at very, very high speed. So to transfer the sector into the buffer, that doesn't take too long. Okay, the seek and the rotational latency, that's what killed the performance of your file system. All right, so the next thing we'll sort of talk about is that, given that, this is how the disk work, how do you really improve the performance of your file system? All right, by the way, there's another terminology over here. It's called cylinder, because what happens is that when you seek to a particular track, you can access all the 8 surfaces simultaneously. You can access one of the 8 surfaces easily. So what you can do is that you can think about all the tracks that are at the same track number, but on different platters. They're actually in the same cylinder. Okay, so over here, there are 8 tracks that belong to the same cylinder. All right? Okay, so some people will say that, well, you're going to seek to a particular head number, a cylinder number, and then, access a particular sector number. The textbook talk about this typical disk. So this one actually sounds really fast for the 1980 standards. It's spinning at 10,000 RPM, revolution per minute. Okay, so I think these days some of the disks on your laptop, they're spinning at the speed. They have number 8 surfaces. The size of a sector is 512 bytes. Okay, so you have a block size that is equal to 2, then every block equal to 2 sectors. Okay, if you have a block size equal to 8 kilobytes, then every block equals to 16 sectors. The number of sectors per track is between 500 and 1,000. Okay, so if you look at this picture, I'm going to delete this. Okay, so you can see that, the inner track over here, okay, their circumference is smaller. Okay, so you will have a smaller number of sectors in the inner track. Okay, the outer track, the circumference is bigger, so you can actually pack more bits into the outer cylinders. Okay, so therefore, the number of sectors per cylinder is actually different, from inside to outside. Okay, so over here it says the inner one, you can pack 500 sectors in them. The outer one, you can pack 1,000 sectors. So on the average, it's about 750. Okay, the number of tracks per surface is going to be on the order of 100,000. Okay, that many, tracks. The storage capacity, if you multiply all these things out, this is a 300 gigabyte disk. Okay, pretty big, for the 1980 standard. The average seek time. Okay, so when you go from one track to another, right, it's going to take you 4, milliseconds. Okay, so what happens is that on the disk head, right, you're sitting right here and you want to go from one place to another. How do you make the disk head go to another place? Okay, so on the hard drive, there's a motor, which is a mechanical device. It's going to move this guy along the track, along some kind of a track over here. So it needs to speed up the motor. Okay, so you need to speed up the motor, and then the motor is going to go on constant speed, and then you have to slow down, right? This is time. Okay, and this is the motor speed. Okay, motor speed equal to 0 if the disk head is not moving, right? So you got to speed it up, go as fast as you can, and then, come down. Okay? Once you come down over here, most of the time, the calculation is a little tricky, that you might not be right at the track that you want, so you have to jiggle a little bit to get to the right place. Okay? So that gives you the average seek time of 4 milliseconds. Okay? 4 milliseconds is a very, very long time. Okay? One track seek time over here says, well, if you are at track number 528 and you want to go to 529, okay, apparently this one takes, a much shorter amount of time. Okay? Because what happens on the disk, there are actually 2 motors. One is the motor that goes like this, and the other one that jiggles a little bit, that's a different motor. Okay? So if you just want to jiggle a little bit, it will take you 0.2 milliseconds. Okay? So this is 80 times, slower than this. Sorry, 20 times slower than this. Okay? All right, so if you have a choice, you want to do one track seek, and you don't want to seek, across the disk. Okay, the maximum seek time going from track 0 all the way to the last track is going to take you, 10 milliseconds, right? Because that one you're going to, ramp it up as fast as you can and go full speed across the disk, and then, try to hit the brake as hard as you can, and that will take you, 10 milliseconds. All right, so these are the characteristic of a typical disk. Okay, so later on we're going to sort of see, how we're going to use this information in order to figure out, how do you really speed up the disk. Okay, so first we're going to see what is the problem with this very, very simple file system that doesn't really work very well. This disk that we just talked about, it has a maximum transfer speed of 64 megabytes per second. Okay, so, so that's pretty fast. But for the system file system, if you measure the average transfer speed on a particular disk like this, you will, come to the conclusion that, the overall read time, okay, is going to be, the maximum speed that you can read is only 124 kilobytes, or 122.4 kilobytes per second. Okay, on a disk, that's, that's 64 megabytes per second. That's the maximum transfer time. Okay, and the reason is because rotational latency and seek time is killing the performance, right? Once you get there, the last part when you need to transfer data from the disk, from the disk head to the buffer on the disk controller, that you can go this fast. Okay, but the rest is really, really slow. And most of the time you just wait there. You're waiting for the disk to go to the right place, and the disk will generate interrupt. When it goes to the right place, it says, okay, I'm there. What do I have to do now? Now go wait for this particular sector, and then when the sector is there, then you read it. Okay, so all the wasted time is killing the performance, right? So basically, the operating system is actually slowing down, the disk system. Okay, you're only using even less than 1% or even less than 0.2% of the disk capacity. All right, so as it turns out that you can actually improve quite a bit, by changing what you do in the operating system. Okay, so this is not a pure hardware. We're going to be using exactly the same hardware. We're going to change the operating system, and then we're going to see how fast we can go with this particular disk. All right, so in come the fast file system. Okay, so the solution that you can do, right? One way is of course to do, to improve hardware, but turns out the hardware you cannot improve that much, but the software make a big difference. So how do you make an improvement in hardware? Well, you can use something, the prefetch buffer in the disk controller. You can use a bigger buffer. Okay, so therefore, whenever you try to read one block, you read 10 blocks. Okay, or you change the block size to be something bigger. That can, speed things up a little bit. Right? But the only thing that you speed up is only the last part. Okay? You don't speed up any of your seek time or your rotational latency. And the seek time and the rotational latency, those are the one that's killing the performance. Okay? So this is going to improve only a little bit. Okay? The software, if you can organize the data structure on disk, as it turns out, that can actually make a big difference. Okay? Some of the trick you can do, you can also help the hardware a little bit by making the block size a little bigger. Right, instead of having, half a kilobytes size sectors, well, I guess half a kilobytes, if you have 1 kilobytes, blocks that will use up 2 sectors, you can make it into 8 kilobytes block. So therefore, whenever you want data, you're going to get a lot of data at a time. Okay, so that can improve the speed by a little bit. What you really want is you want to minimize the seek time and you want to minimize rotational latency. Okay, so those two, turns out, you require some special tricks to speed those things up. Okay, so the next improvement of the system file system is called the fast file system. Okay, fast file system, I think the last lecture I mentioned already, this is a very important file system, because lots of the Unix file system are based on the fast file system. The Linux ext234, they are based on the fast file system. Solaris file system is based on this. All right, so what it does is that, it tries to improve the performance of the disk. They also have some additional features. For example, so this is not related to performance. They support longer component name in directories. Okay, in system file system, the file names and stuff like that, they can be very short file names. So later on, they found out it's really not convenient. People really like long file names, especially if you own a Macintosh. If you own a Mac, you probably have really, really long file names all the time. So, they try to support, longer file names. We're going to see how that's supported a little later. They basically had the same kind of disk map as system file system. Okay, so so the main changes is on the layout of the disk. Okay, where do you put these blocks, etc., which we're going to see next. All right, so the obvious thing to do is to have a larger block, right? So this way, when you try to read the data, you're going to get a lot more data at a time, so you don't have to go to the disk as often, right? If you have a small files, maybe you put everything in one block, you just one disk read, and then you're done. Okay, so that helps a little bit. Okay, but the problem with having a larger block is the following: is about a fragmentation, right? Okay, remember the minimum allocation size of the file system is a block. Okay, so the larger the block, the more likely you're going to have wasted space, right? If the block is small, if you have a block that's this big, now if you have a file that's actually this big, okay, how many disk blocks do you need? Okay, well you need you need a few. Okay, and then so in this example, you get 1, 2, 3, 4, 5, 6. 6 is not enough to hold the block, so you need the 7th, right? When you use the 7th, then you're going to end up with a little extra space. Okay, so this is internal fragmentation or external fragmentation. Right? Remember, external fragmentation meaning that the not usable blocks are outside of the allocated blocks. Internal fragmentation, it means that the not usable space are in the allocated block. Okay, so in this case, you will allocate 7 blocks, okay, to hold the entire content of the file. Okay, so therefore, this space is not usable, and they are within the allocated block. So therefore, by definition, this is internal fragmentation. All right, so if you have a small block size, the most amount of internal fragmentation you can have per file is pretty much the size of the block. Right? The worst case is that this one is going to be 6 blocks plus 1 byte. You're going to end up using 7 blocks, so you're going to, wasted all the space in the last block. Okay, now if you have larger blocks, what's going to happen, right? If you have larger blocks, now you're going to end up with wasting a lot of space. Okay, so what's wrong with this picture? Right, if every file is like this, if every file in your file system is like this, what is the utilization of your, entire disk? 50%, right? Because half the disk is wasted, right? Okay, so this is a really, wasted disk space. Okay, so the file system try to use the larger block size, and they realize that you don't want to waste 50% of your block size. So what they do is they come up with a solution where you actually have 2 block size. Okay, you can allocate blocks either in the large block size or in the smaller blocks. Okay, so in that case, if you have a file that looks like this, you will actually allocate the large blocks. So if you have a large file, you will actually allocate all the beginning part with the large blocks and the last one with small blocks. Okay, so this way you will minimize, your overall wasted amount of space is going to be pretty much the same as the previous scheme. Okay, so this is the basic solution. Okay, so they have a bunch of rules. So in the beginning, you need to determine the number of fragments per block. Okay, and this is fixed at the time you configure the file system. So when you create the file system, when you make the file system, you have to decide, one of these large blocks, how many small blocks can it be broken down into. Okay, once you make that decision, you're stuck with that number for the lifetime of the file system. All right, and then of course when you allocate a file, the beginning part they all have to use large blocks, and the last block you can use many small blocks. All right. Okay, so you can end up even with a situation like this. You have 2 files. One file takes up, 2 big blocks and 2 small blocks, and the other one will take up 1 big block and then, 4 small blocks. Okay, so now if you try to grow a file, if you take this blue file, you try to append to it, you're going to start using more blocks over here. Then you actually have to get your own block in order to start doing something like that. All right? Okay, so again, over here, you trade off. What is the trade-off, right? You try to save space, okay? So you're going to spend more time managing your file system. Okay, so now when you try to, create a new file, you have more options. So you need to do more calculations, and you need to probably copy blocks around. All these things are going to take time, right? So again, it's a good old space-time trade-off. All right? So is this the optimal way to go? Well, we don't really know. It really depends on what kind of files you're putting on that particular system, right? If every file that you put on a system, they all just happen to be multiples of the block size, well, then that would be perfect. but in reality, you don't really know how things are fragmented. Okay? It depends on what the user put on them. All right, so that's one thing that it does, to use the larger block and try to also minimize internal fragmentation. How do you minimize seek time? Okay, so the key is that to notice that for the Rhinopia disk, right, when you do the average seek time is 4 milliseconds, but when you seek to the next track, it only costs you 0.2 millisecond. Okay, so in a way, you always want to just seek to your neighbor track. Okay, you never want to go seek across the disk. Okay, which means that if the disk is sitting somewhere, okay, I just want to access the track next to it. Okay, so how do you do that? Okay, so it turns out that, yeah, you have to really plan things out so that when you are accessing the disk, you're sort of accessing a bunch of stuff at a time, and they're all right next to each other. Okay, so you have to organize the disk in a special way to put all the stuff that you tend to put all the files that you tend to access together right next to each other. Okay, so remember when I start talking about how do you allocate a block in the system file system, it's sort of kind of a random allocation, right? If you need a free block, oh, just grab the first one on the list. Okay, that's really not a good way to go. Okay, that you're going to end up with the blocks all over the place, and you have to perform seek all the time. And that's why, you know, you only end up using less than 1% of the disk performance. Okay, so you have to carefully plan to put all the files that you want to access together right next to each other. So when you try to seek from one track to another, it will only cost you 0.2 millisecond instead of 4 milliseconds. Okay, so you want to keep the related stuff close to one another. Okay, and you want to separate stuff that really have no relationship with each other. Okay, so what does that, you know, what does that lead to, right? So the idea over here is that you want to, you know, change your disk, you know, have different kind of organization. You want to put stuff that are right next to each other. You want to form, over here it's called cylinder groups. Okay, so every cylinder group has their own allocation. Okay, so remember in the beginning, it's the system file table. Okay. If we look at the file system, right, here is the boot block, here's the super block, here's the IList, and then here are the data blocks, right? Okay, so we're going to organize a little differently. We're going to do something like this. Okay, so this is, if this is still our entire disk, right, here is the boot block, and here's the super block. Okay, and then we're going to divide disk into, you know, cylinder groups. Okay, here's the cylinder group number 1, cylinder group number 2, cylinder group number 3, okay, etc. Within every cylinder group, we're going to have an inode list, and we're going to have a data region. Okay, so now a bunch of files that are related to each other, we're going to put them all in the same cylinder group. Okay, another bunch of related files we're going to put in a separate cylinder group. Okay, so that when you need to look for stuff, you know, they're all right next to each other. Once you start working on a particular file in a cylinder group, all the other files are right next to each other. Okay, so when you allocate, right, when you want to allocate, when you want to look for a free block, you don't look all over the disk for free block. You only look for the free blocks that are close to wherever you're working on. Okay, so this way, hopefully, you only have to use, you know, the small seek time. All right, so. Okay, so how do you allocate these cylinder groups? As it turns out that, you know, there's really, you know, I mean, you can write an optimization equation and try to, you know, I guess those engineers, right, writes, you know, lots of, you know, equations, and you say, you know, maximize this under the constraint, this and that. You can compute them, but as it turns out that if you do something like that, then things are you know, your design will be very fragile. And every time something changes, you have to recompute everything, you have to reallocate everything, and that's really too expensive. Okay? So usually in computer science, we try not to do that. Okay? We try to sort of have a high-level design that are pretty good. Okay? So you don't have to run this optimization routine over and over again. Okay? We end up using, you know, heuristics to try to, you know, make reasonable, to use good heuristics. Okay? Even though we cannot prove that these heuristics are optimal, but, you know, by you know, running simulation, by experimenting on the system, we find out that, you know, what actually works. Okay? So in practice, there are actually, you know, a bunch of rules for, you know, putting things together. Okay, so here's an example. If we have a directory tree like this, okay, what would you put together? Okay? So remember that, right? If you recall what a directory is, Okay, if I have a directory, if this is a directory, okay, a directory is just a mapping of file names to inode numbers. Okay, so therefore, if I open up a directory, why would I want to open up a directory? Well, it must be I want to work on the file underneath it, right? Okay, or if you are doing, ls or something like that, when you open up the directory, look at the content, well, you want a listing of all those contents. Okay, so therefore the tendency is that, it might be a good idea to put all these things inside one cylinder group. Okay, is that the best thing to do? I don't know. Okay, but, that's a heuristic that we can go with. Okay, so you'll put these guys together and these guys together. Okay, maybe if you are even trying to be even smarter, you say, oh, these are the .c files. So therefore, if I have a bunch of .c file, one of the things I would do is that I would do make inside this routine. I will end up opening up all these files. So therefore, I want these things right next to each other. Okay, so it's reasonable to put all these things into one cylinder group. What about this guy? Okay, so in the end, you still have something left over, right? Maybe you have to group these guys together and put them into one cylinder group. Okay, so it's kind of a difficult choice to decide whether this directory and this directory, should they be in the same cylinder group or not? Okay, so again, over the years, people sort of develop heuristic to say that, yeah, maybe you shouldn't put it here. When you try to create a subdirectory, put a subdirectory in a different cylinder group and find a cylinder group that has a lot of empty space and, put it there first. Okay, and you want places with a lot of empty space because, you might end up adding more files into that directory. Okay, so anyways, these are the sort of the heuristic on the previous page, and we're going to end up with different kind of allocation. Okay, when you start doing something like this, okay, all of a sudden you're going to find out the way that you're going to use the file system is that you tend to, actually use all these files together, and then you do expect the performance to improve. Okay, all right. As it turns out, if you just do these two tricks. Okay, actually, the second trick, using the cylinder group, it will actually give you a 20-fold improvement. Okay, so the Rhinopia disk, starting from system file system, using less than, 0.16 of the file system, 0.16 of the disk transfer speed. Okay, and now you're going to improve to use 3.7% of the maximum performance of the disk. Okay, that's still terrible. Okay, but it's 20 times better than before. All right, so how do we get it to even better? All right, so does this one solve the problem of rotational latency? Well, kind of, right? Because now, if you only access things to the cylinder group, you only do small seek time. Once in a while, if you have to go to a different part of the disk, well, what can you do? You have to go to a different part of the disk. Okay? What you try to do is to minimize those regular seek operations. You try to only, do seek to the next track. All right, so the next thing that you can do is, what about rotational latency? Okay, so if I have a disk that spins this way, okay, so over here this is going to spin this way, and if I put a disk head right here, okay, I'm going to have the disk head seek to the right track, okay, and now the track is going to, come under the disk head, okay, so if the disk is spinning this way, actually, I guess my disk head is in the wrong place. It's sitting here, okay, looking at the beginning of sector 1, right? This is sector 1, 2, 3, 4, 5, okay, and it's gonna the disk is gonna spin this way. So if your head is right here, then you're ready to transfer the data from sector number 1 to the disk controller. Okay, so what's happening, with the regular disk, right? If you have the sector one after another, okay, when you finish transferring the sector, to the disk controller, what does the picture look like? Okay, I mean, I can't really spin this picture on the slide, so what I'm going to do, I'm going to move the disk head. Okay, so after you transfer all the data to the disk controller, now the disk head is going to be sitting right here, right? Okay, it's ready for the next track. Okay, but now what's going to happen, right? You generate interrupt to the operating system. The operating system look at it and say, oh, I need to read the next track. Okay, at that point, the operating system will tell the disk controller, or the device driver will tell the disk controller to say, hey, now get me sector number 2. Okay, so all that time that was elapsed on the disk, how long does that take? Okay, it probably doesn't really take no time. It takes some time. By the time you're ready to read sector number 2, your disk head might be right here. Okay, if your disk head is right here, can you read sector 2? Well, you really can't read it, right? You have to wait for the disk to spin the entire revolution until the disk head is right at the head of sector 2 before you transfer sector number 2. Okay, same thing happen when you finish doing sector number 2, your head is right here, but now you have to interrupt the processor. The processor might have this interrupt disabled, so it will not handle the interrupt, right? Remember what happens in the interrupt. Inside the interrupt handler, you unblock a thread, and you start the next disk operation. Okay, so the next disk operation is read sector number 3. By the time the disk controller gets read sector number 3, again, the head is right here. Okay, so therefore you have to wait another 1 revolution. Okay, so if you start doing this every time, even if you're reading consecutive sectors on the disk, right, one block will have many sectors. Okay, so when you read consecutive sectors on the disk, every time you have to wait for an entire revolution. Okay, so this is why the disk is so slow. Okay, because the layout on the disk is wrong. The sectors shouldn't follow one after another. They should probably have some gaps between them. Okay, so therefore, what is the solution? Right, the solution is to lay out the disk a little differently. Okay, so for example, if your disk, if you know that every time when you
The time is 1 o'clock.
seek to when you start the next operation, your head is right at the beginning of the next track, then maybe the right thing for you to do is to interleave the sector numbers. Okay, I mean if you're at the beginning of the next sector, but you passed it already, then you have to interleave the sector number. You want to number this one sector number 1. You want to skip something, skip 1, and then number this one sector number 2, and number this one sector number 3. Okay, so this way, when you finish reading sector number 1, right, you generate an interrupt, and the interrupt tells you to read sector number 2. By the time it gets there, your head is right here. How long do you have to wait for the sector number 2? Not that long, right? You only have to wait until, it gets right here. Okay, so you don't have to wait for the entire revolution. All right? So you can actually, so what happens is that when you create your file system on disk, you can measure the disk to see, how many blocks do I have to skip before I number the disk block consecutively. Okay, so this way I can time it so that I can create a file system for minimum rotational latencies. All right, so how much does that buy you? Okay, so it turns out that if you just do that, do the block interleaving, right? This trick is called block interleaving. So if you interleave the block, you're going to get a factor of 15 improvement. All right, so going from 3.7% to 15 times better. Okay, so now you end up using almost 50% of the maximum disk capacity. All right, so larger block size buy you a little more, okay, but cylinder group and block interleaving buy you quite a bit. Can we do better than 50%? I mean, should we go for better than 50%? Of course, we should always go for 100%, right? We want to have maximum transfer speed of the disk. All right. Okay, so, right, over summary, right, system file system, 0.16 of the capacity, FFS without block interleaving, 3.8%, and now it's go to 50%. Okay, so software makes a big difference. All right. This one has X in it. This one has X in it. So by the way, so other operating system, other file system use different kind of things. Windows has very different way to organize data on disk. Windows actually don't use blocks. They use something called extents. Okay. So for example, here is one file. A file has a run list. Okay, and the run list records all the blocks, all the data bytes for that particular disk. Okay, all the bytes for that file. Okay, so for example, this file consists of several run lists. It has 8, I guess over here, so maybe it has 8 sectors that are consecutive. Okay, so over here there are 8 sectors starting at offset 117A2, right? So that's one of the sector number. Okay, so starting from here, I have 8 consecutive sectors for the first 8 sector of that file. Okay, and then after that, the next a sector 8 for that belongs to that file starts over here, start at offset 10624 for 10 more sectors. Okay, and then, there's more, et cetera. Okay, so, and every sector, I guess what that is, right, this is 412 bytes, et cetera, so you can actually keep track of stuff this way. Okay, so this is called extents. Okay, and the allocation methods for allocating extents is what? Right, so you can see that, this particular file consists of a bunch of little blocks. Okay, well, actually not little blocks. These ones, you can call them runs. Okay, here's one run of 8 blocks, and here's another run of 10 blocks, and maybe there's another run of 15 blocks, etc. Okay, so the file is put together by a bunch of runs. Okay, and these runs are spread, can spread all over the disk. Okay, so the basic allocation scheme is, either first fit or best fit. Okay, so you can think of the disk as a bunch of sectors. Okay, they are maintained just like in memory allocation in a free list. And when you try to allocate stuff, you can use a very similar kind of allocation scheme, for allocation scheme for disk blocks. All right, is this good for sequential access? Well, it's not so bad, right? I mean, when you want the beginning part of the file, you go here and you start reading this sequentially. And then when you're done with this one, you want to go to the next one. You already know where it is because this one you already have read. Okay, what about this one for random access? You have a really large file. I want to seek to, the 100 megabytes offset from the beginning of the file. Okay, that's going to be a problem, right? Because basically I have to, if this one is consisted of many, many little blocks, I might have to go through many sectors to get the entire run list, and I have to access them sequentially in order for me to get to the place I want. There's no way for me to do some simple arithmetic to tell me which pointer to access, okay? Because every one of these guys, the run length, it might be different. So I have to walk down this entire data structure on disk in order for me to find out where I need to go. Okay, so this is terrible for random access. Okay, to make things a little better, you can actually do things using a hierarchical data structure, right? Anything that is a linear list is really not scalable, and the way that we can make things scalable, right, in data structure class, there are only 2 basic approaches, right? One is to use a hash table, and the other one is to build a tree. Okay, so Windows basically they can use a tree. And they use a tree in order for you to keep track of the data structure. So in this way, if you go to the root of the tree, then that will, if you want to do a seek, that will tell you, which sublist to look for. Okay, this way you can cut down a little bit on the time to search for a particular block. All right, so we're not going to talk too much about, again, Windows. Okay, so. All right, so the next thing that we're going to talk about is that, how do we hit 100% of the disk performance? Okay, well, 50% sounds pretty good, but, if we can do better, why not? All right, so one of the problems that we have right now, is that, the files are all over the place. Okay, and in order for you to go from place to place, well, you got to do seek. Okay, and then when you do seek, whenever you do any kind of seek, right, the seek time is overhead. Right? It's completely waste of time. Okay, so you got to sort of make sure that maybe there's a way to sort of absorb all that kind of time. Okay, I guess for those who in EE, right, you learn pipelining. Well, pipelining is a way to sort of amortize the time that you're doing one thing and you spread it among several tasks that are sort of sharing the same hardware. Okay, so we can play those kind of tricks to try to make the performance of the disk to appear to be faster. All right, so the file is scattered all over the place. So let's look at what we have in terms of this higher level picture. Okay, sort of at the higher level abstraction, right? If we have a file, okay, the file level has abstraction. Like for example, if we have a file, this one could be a PDF file, could be a GIF file, could be a PNG file, whatever. This one, let's say this file is 5 kilobytes long. Okay, and these blocks, they're going to be spread all over the disk, right? If we have a system file system, all right, over here it says, well, we're going to allocate an inode. The inode is going to keep track of these 5 blocks. Okay, with the system file system, the inode belongs here, and the data blocks belong to the data region. Okay, and we said that that's really poor performance. Okay, when we go to the fast file system, okay, now the blocks are a little bigger, right? So maybe we'll, if we have 4 kilobytes block, then we need 2 of these guys, and they are all allocated within the same cylinder group. All right, so this gives us, 50% of the speed, right? So we're going to see, how do you really get around this to have a better performance? All right, so one thing that helps over the year is that, so we have this picture in terms of, technology. Okay, so this time is, years. Okay, in the good old days, everything is slow and everything is expensive. The disk was actually at a point they are faster than memory. Okay, so in the good old days, the disk is actually, so over here it says the speed of this disk, and then the capacity of the disk, they're on this particular axis. Okay, so in the good old days, the memories are very, very expensive. So on a system, you can actually have very little memory and have lots of disk. Is this still true these days? I mean, think about your laptop, right? I mean, it's still kind of true, right? Your disk could be a 1 terabyte disk. Your memory might be 4 gigabyte. Okay, but sort of the gap is a little is kind of closing, that we have a lot more memory. Okay, if you think about your laptop, if it has 4 gigabytes of memory, what's stored in those 4 gigabytes of memory? I mean, if you're running, if you're running your warm-up one, how much memory does it take? Nothing, right? If you're running your warm-up 2, how much memory does it take? Well, pretty much nothing. So why do you need all this memory? Okay, so that's related to this particular picture. As memory starting to become, for the same price, you can get higher capacity and higher speed. Then we're starting to can put more memory into the system. Okay, and then, then lots of people manufacture this. The price keeps going down. So the disk over the years, they still use the same technology. The hard drive is still the same technology. I mean, these days we have different technology. We have SSD, but still the most cost-effective way to store stuff, right, is the hard drive, right? You can buy, I don't know these days, you can buy, a 4 terabyte, hard drive for a couple of $100. Okay, so, price performance-wise, if you want to store a lot of data, the disk is still the best way to go. Okay, but as the CPU gets faster, and they also, they can do a lot more operation, we sort of we're in this particular region now. Okay, so once we're in this region, we can have a lot of memory in our system that actually give us the new approach to deal with the disk. Okay, and that particular approach, over here, we're going to call it aggressive caching. Okay, so by the way, we're using the word caching over here in the sense of a computer science word, cache, not the double E word cache, right? Double E, if you take, the architecture class, right, they say the CPU has a cache, and these cache, set associative, 4-way set associative, 8-way set associative, stuff like that. It's not that kind of cache, okay? When we talk about cache, it's like the I know cache that we talk about, okay? That you just have another copy, somewhere, so that when you try to look up something, you go to the cache first to see if you know that information or not. If you don't have that information, you're going to fall back to the original place where the data is stored, and you look for that. Okay, so in a way, it's like, all right, so in the hardware class, right, you have CPU, okay, and then you have main memory, right, and the stuff that you put between over here, you call it cache, right? Okay, and this cache, we call it cache is because they cache the data from main memory. Okay, so when you need to access main memory, you're going to see the data is in the cache first. If it's in the cache, you go ahead and access it. If it's not in the cache, you're going to, you're going to go to main memory, have the main memory to bring data into the cache, and then you access it. Okay, similarly, we're going to do the same thing. We're going to have the CPU right here, okay, and over here we have the disk. All right, and inside over here we have main memory, and we have lots and lots of main memory. Okay, so instead of going to the disk all the time, right, that's what kills the performance, right? Anytime we have to go to the disk, we have to do a seek, rotational latency, it's really, really slow. Okay, what if we can read the entire disk into memory? Well, first of all, is that possible? I mean, your laptop is not possible, right? You have 4 gigabytes of main memory over here, but this one, is 500, 500 gig. So, of course, it doesn't fit. Okay, but think about all the stuff that you're running on your laptop. Okay, do they actually take up 4 gigabytes of memory? Maybe not, right? Okay, so what if I take everything that I want from the disk and all read them into memory? Okay, memory is cheap, they are fast, they have high capacity. Okay, so therefore I can actually have enough stuff for everything that I need on the disk that I need from, from now till I shut down the computer. Everything I need, I can put it over here. Okay, so this become my cache for the disk. Right? So now memory, my main memory become the disk cache. Okay, so in that sense, every time I need to access the disk, I look into the disk cache and see if the disk data is there already. If it's there already, I don't have to go to the disk. I just need to access memory. If it's not if it's not in the disk cache, then I will go to the disk, ask the disk to transfer data into the disk cache, and then I will access the disk cache again. Okay, so this I can aggressively cache everything I need into into the disk cache. If I can do that, okay, if I can do everything I need in the disk, what is my seek time? Well, it will be 0, right? Because, everything I need, every time I try to access that data, it's already in the disk cache. I don't have to seek. So seek time becomes 0, rotational latency becomes 0, transfer time becomes 0. How can that all be 0? I mean, you still need time, right? But the thing is that, when we are doing other stuff, when we are serving other threads, one thread is blocked inside the kernel, waiting for disk transfer, while we're doing useful stuff, inside the kernel. So therefore, if you average out all the disk operation, on the average, the disk access time is 0. Because we always are busy doing something else. All right, so this is why, the operating system, we sort of need to serve, lots of these processes so we can actually mask out the poor performance of the disk, okay, by reading the, as much data from the disk into memory ahead of time in anticipation for all the disk block that we need. Okay, so this way, when we try to access the disk, we always get, when you try to look for data, it's already in the cache. It's called a cache hit. Okay, if the cache hit is 100% cache hit, that means that you never go to the disk. Okay, if your cache hit is 99%, that means that 99% your seek time is equal to 0, your rotational latency is equal to 0. 1% of the time you still have to go pay the disk to do a seek and do a rotational latency. Okay, but then the average access time will be 0 times 99% plus 1% of the time you pay on the disk. Okay, so you can see that if the disk cache has good performance, then the average rotational latency is going to be, cut into, 100% of what it actually is. The rotational latency also going to be cut into 1% of what it was. What if your cache hit rate is 99.9%? Okay, then it's going to be 1/1000th of the seek time and the rotational time. Okay, as you increase the performance of your disk cache, then, all the, it's going to appear that this is really, really fast. All right, so that's the basic trick. Okay, so this particular approach is called, you call a buffer cache. Okay, so a buffer cache is this memory that you use in the file system. Okay, and I guess the modern system, Linux or something, Linux, half the memory is probably used as disk cache. Okay, so you actually use quite a bit of memory for the buffer cache. Okay, so therefore, if all the data that you need are in the buffer cache, when you try to read from the disk, you gotta, so how do you read from the disk? Right, you call read, right, read, okay, file descriptor, buffer size, right? Okay, you're gonna check the buffer cache to see if the current cursor position, starting from that point on with that many bytes, are they in the buffer cache already? If they're in the buffer cache already, you got a hit. Okay, so therefore, you don't block in the file system, you return with the data right away. Okay, if you have a miss, then, your thread get pushed to sleep, and then the disk, invoke the disk driver, transfer data, all that kind of stuff. And eventually, when that data in, and when you have a miss, okay, and you get a chance to go to the disk, how much data do you bring in from the disk? As much as possible. Okay, so you try to sort of fill up the cache as much as possible, right? If you go to read the first block of your file, bring in the entire file. Okay, and as soon as you finish the first one, you will return, right? And then the rest of it, they keep coming in. Okay, so therefore, inside the file system, there's a subsystem just dealing with the buffer cache. Okay, and try to fill up as much of the buffer cache as possible. Okay, so that when an application tries to read the disk, you're going to get a hit. All right, so this way we can actually reach almost 100% of the transfer time of the disk. All right, what about, well, so reading is, is easy, right? What about writing? Okay, when you write to the disk, you don't write to the disk anymore, right? You write into the buffer cache, okay? But, when the write returns, your application assumes that the data went onto the disk. Okay, so this is really bad, right? Because right now, if we lose power or something like that, right, then the data doesn't get to the disk. Okay, so when you come back, reboot the system, you say, hey, how come the disk still have the old data? Okay, so the problem with the buffer cache or with any kind of a cache is that, if you update the buffer cache, then you need to also update the disk. Okay, so when do we update the disk? Right, so there are different approaches. One is called write through, right? Whenever you try to write to the buffer cache, you wait until it completely writes to the disk, and then you return. Okay, so in that case, read is going to get very good performance, but write performance is going to be just as bad as before. Okay, you're going to have 50% of the disk throughput. Okay, so that's, that's okay. It's not great. Okay, so the usual approach is that, you're going to write directly into buffer cache, and inside the buffer cache, there's going to be a daemon process running. That, the process of that daemon is going to keep write data out to disk. And what's the name of that daemon? The page out daemon, right? Okay, so in kernel 1, there's something called page out daemon. Part of that job of the page out daemon is to write blocks like this. So when you write to a particular block, okay, what you do is that you make the disk block dirty to say that this block has been modified. A block has been modified. That means that the block inside the buffer cache is different from what's on the disk, so that it needs to be written to disk. Okay, so you mark all these blocks that are dirty. Okay, so when the page out daemon, got a chance to wake up, it will scan the buffer cache to look for all these kind of blocks, and they will write it to disk. As soon as they finish writing to disk, they will clear the dirty bit, because now this block is no longer dirty because it's the same as what's on disk. All right, so this is how you make these two things to be the same. Okay, so how often should you wake up the page out daemon? Well, so that's kind of tricky, right? Because if you wake it up, very, very often, okay, then you're going to end up with, doing a lot of disk writes, okay? And, you're going to end up waiting and stuff like that. So it's not going to be very efficient, right? So you do want to wait as long as you can, because the longer you wait, you can sort of write out the whole thing in one shot as much as possible, okay? You can probably group things together so you can minimize write, right? So if you write it often, then that's really not good. But if you write it not very often, then you risk, having a crash in your operating system, and you end up with the system being inconsistent. Okay, so in a modern system, do you have to worry about you have a crash in the operating system? Well, you do, right? Because you see some people with really bad habit, right? When they leave their office, they unplug their machine. Okay, so that's the worst kind of crash. Okay, so you sort of need to write this often enough, right? Maybe once per second, once per 5 seconds, once per 10 seconds. It becomes really, really risky. All right. So that's one way to deal with it, right? But, it's not really, it's not really a great idea, okay? So now we're going to look at a different approach, try to speed up the write. Okay, so write is still a problem, right? Because over here, no matter how, no matter how you decide to write, there's going to be a window of vulnerability, okay, that if you get a crash, you won't be able to recover. Okay, so I guess in the next set of lecture notes, we talk about crash resiliency, and we're going to talk about that after Chapter 7. We're going to see the real way of dealing with that. Okay, so right now we're sort of not going to worry about crash too much. Okay, we're going to sort of try to think about how to improve the write performance if we want to write to the disk. Okay, so the basic idea over here is that when we try to write to the disk, we want to write as many blocks in one shot as possible. We basically want to use sort of a smart disk controller and tell the disk controller to say, well, here's 1,000 blocks or 1,000 sectors. Write them all to disk in a consecutive way. Okay, that's the fastest way to write, right? Because what happens is that you pay for seek only once, rotational latency only once, and then you're gonna write 1,000 sectors. Okay, so that's the best way to write. Okay, but what kind of file system do we have that will allow you to do that? Okay, the fast file system doesn't allow you to do that, right? Because the block within the cylinder group, well, they're still scattered all over the place. Okay, so we actually need a different file system that will allow you to do one long write. Okay, so that particular file system, okay, is called the log structure file system. Okay, so the goal over here is that, you want to do one long write. So how can you do that? Okay, so you gotta have a weird file system. So the file system is like a log. Okay, if you have a log, is like a journal, right? If you have a journal, do you write in the middle of the journal? Right? If you have a journal that you write, right, it's append only, okay, and it's never delete, right? I mean, that's a real journal, right? So the main principle for a log structure file system is that you never delete anything. So you have a file system, you never delete anything, and then you have a file system that appends only. Okay, so therefore, if you want to access this file system, right, the disk head is sitting right here. Okay, you want to perform a write, you write, a long record, append to the current log. Okay, so then you're going to end up writing very, very fast on the average. Okay, so because this could be a write of 1,000 sectors, but you write it in one operation. Okay, so therefore, you're going to improve the write performance by quite a bit. Okay, so what do we write on this thing, right? So this picture showed that, if you want to create a new file, I got to write the new inode, the new data, right? Because I can't really, it's append only, so I can't go over here and modify some other parts of the file system. Okay, so the file system actually going to look very, very different. All right? Okay, so let's look at, how to implement this, right? How does never delete and always append, how do they help with performance, right? They minimize seek latency and minimize rotational latency. And there's an implementation of it from Berkeley. It's called the Sprite file system. Okay, I think that's one of the, it was the first one in somebody's PhD dissertation. They implement the file system and they use it. So we're going to see how this thing actually, improve, write performance. Okay, so the idea over here is when you try to write, you make a one long write. All right, so if we have a log structure file system, right, if you have a file, so we're going to take an example, try to explain, what the log structure file system do and what kind of special thing does it do, right? So the idea over here is that you have a file. The file has an inode, right? So the high-level abstraction still doesn't change. Okay, inode contains this map point to this block, right? So at the high level, we still have this. Okay, so now when you create a file, it gets appended to the file system. So therefore, it tends to sit, somewhere at the end of the log. Okay, so this example, I'm going to write the data block first, and then, finally write the inode block. Okay, so over here, data block, when I write, I get a block number. Okay, that's the block number. I put them into the inode, right? That's why I write the inode last. Okay, so let's see how this thing get evolved. Okay, if we have another file, okay, so let's call this one file A and this one called file B, right? File B get created later. It only takes one disk block. So here's the block and here's the inode that goes with it. Okay, and now what we want to do is that we want to append to file A. Okay, I want to modify the file. So we're going to see how, never delete, append only actually work. Okay, so over here, we're going to use the data structure called the inode map. Okay, so inode map is kind of a conceptual idea. Inode map basically tells you where all the inodes are. Okay, so over here, inode A is right here, and inode for file B is right here. So over here, I'm going to keep a data structure called the inode map. And that data structure is actually distributed. They get distributed all across the disk. Okay, so I need something else to keep track of it. Okay, so anyways, I'm going to have a map that keeps track of every file where is the inode for that corresponding file. Okay, and now I want to append to this file. Okay, I want to make this file bigger, right? So in order for you to make this file bigger, what do you have to do? Okay, so in this case, I'm going to append. We're going to append to file A. So this guy is going to get bigger, so this block needs to get bigger. Okay, when it gets bigger, what it will do is that it will need to get a bigger block right here. Okay, so we're going to sort of conceptually allocate a block over here to be bigger. Okay, and then this one, we're not going to use it anymore. Okay, the pointer that used to point to this guy now needs to point to this block. Okay, but if we want to modify a pointer over here, are we allowed to modify a block? No, it's append only and never, you can never change anything, right? So therefore, we're going to allocate this new inode in the end over here. Okay, so this inode, we're going to copy the entire content over here into this inode, and then now this pointer will point here and this pointer will point there. Okay, so therefore, when we, when we need to, append to that file, right? We're going to get a new blue block over there, and then we're going to get a new inode at the end, okay? And then, you know, all these pointers will get pointed to the right place, right? So now this file A over here, this is going to be the first block, and this is going to be the second block, right? Everything is fine, right? Except the inode map is wrong. Okay, so the inode map right now, maybe I shouldn't say A prime, is that A will now point right here. Okay, so now if I have a inode map like this, okay, then I can find all my files, right? Because they all point to the right inode, and the inode keeps track of all the data blocks. Now I have the entire file system. Okay, but what about the inode map? And the inode map needs to store on disk, right? Because when I shut down the machine, everything needs to go on disk. Okay, so the inode map needs to change, right? And where's the inode map? Well, again, right, inode map belongs to the file system, so therefore it's, you know, it's append only, never delete. So that gets kind of tricky. Okay, so the solution for this particular problem, right? Eventually, you have to go all, you know, every time you try to not modify anything, you're going to do append only. So you got to say, well, something else has to keep track of it. And then eventually you have to go to the root of this, you know, dependency. In the end, something has to go somewhere else. Okay, there has to be something that's not part of the log. Okay, so as it turns out, the inode map is part of the log. So therefore, when you update the new location of A, you have to say that, well, now A has a new location. I have to write the inode map right here. Okay, so therefore the picture becomes this. Okay, the inode map that keeps track of file A and B is now the new A is going to be pointed right here, and the B is still pointed to the old place. Okay, now this becomes a piece of the inode map. Okay, so the inode map is going to divide into pieces. Okay, one piece here is the old piece of the same inode map that was right here, and now, you know, this piece get moved to the end because one of the file has been modified. You got a new inode, so therefore this piece has to be written out over here. All right, so you used to have something that points to the inode map piece that was right here, and now this guy needs to point right here. What about this guy? This guy also being updated. All right, so eventually something, we can't keep appending everything. Okay, something needs to go somewhere else. All right, so this somewhere else is called a checkpoint file. Okay, so what happened is that on this particular disk, we're going to have another region that are reserved. So maybe that region is at the, at the end of the disk. Okay, we're going to have two checkpoint file 1 and checkpoint file number 2. All right, one of the checkpoint file is the current checkpoint file, and one of the checkpoint file is the old checkpoint file. Okay, so let's say that this is the old, this is the current. Okay, the current will keep track of all the inode map pieces. Okay, so this one, keep track of this one, right? It used to point here, and now it points here. Okay, it also points to all the inode map pieces. So therefore, can it find the entire file system? Right? If you have all your inode map pieces, then you can find all the inodes. So therefore, you can find the root, and then you can find everything from there. Okay, so this one basically points to the current file system. The file system starts over here, and you can find everything there. Okay, so whenever you need to look for a particular inode, system file system says use the ilist, it's an index or something like that. But now you have to go to this particular structure, right? Inode number 72 now moves around, in the disk all over the place. Okay, so in order for you to find inode number 72, you have to go to the checkpoint file and look for the location of inode number 72. All right, you cannot use an array index anymore. Okay, so now you can find this guy over here. All right, so over here, this one tells you where all the inode is. Okay, so once in a while, what happens is that, so you're going to do a few of these operations, okay, at a convenience time. So for example, you just finished one long write, you update 1,000 files, okay, and all the inode map pieces go down here. You update all the checkpoint file pointer right here. Okay, and now you're at a point, where you can actually take a snapshot of your file system. Okay, how do you take a snapshot of your file system? All right, it's very easy. I do a mem copy, CF1 to CF2. Okay, I copy this entire stuff over here. Okay, so now CF2 is going to be equal to, the anaconda is going to be equal to CF1. Basically, if you follow all the pointers over here, you have the entire file system, right? Okay, and now what I'm going to do is that I'm going to call this one current. call this one old. Okay, or actually I don't have to switch it. I can keep this one old, but now this is the backup file system, and now this one is going to be the current. Okay, from this point, so I just perform a checkpoint operation, and all the checkpoint operation does is to copy this one to this one. Okay, I have a backup file system over here. Okay, and now I can start going, so let's forget about switching the old and the new. This one is always the old, it's always in the backup, and this one is the current one. If I continue to update, the fashion that I've described, then checkpoint file 1 is going to keep moving forward in time, have a newer version of the file system. If I have a system crash, what happened? If I go to this one, if I go to the old version, the backup version, do I have a complete file system there? I do, right? The entire, if you follow all the pointers over here for all the, you're going to find all the inode map pieces. Okay, therefore you're going to find all the inodes. All the inodes is going to be in a consistent state, right? So therefore, if I follow all the pointers over here, I have a good file system. So if I have a crash or something like that, I just copy everything old to everything current. Voila, I finished my recovery. Okay? Even though, the stuff that hasn't been written out to disk, right? Even though some of the stuff that have been written out to disk, if I did this before I update the checkpoint file, all the stuff that I have written out to disk, there's no way to reach it because I'm using my old version of the file system. Okay, so if I do this once every, second, once every 5 seconds, okay, so you know that if you're updating a file and all of a sudden somebody unplugged the power cord, you don't really expect the file that you were editing just now. You just type in one last character, you don't expect the last character to go into the file system, right? Okay, so therefore you know that, during the last 1 second, maybe something got lost, but all the stuff that you've done before, well, they're on the disk. Okay, so therefore using these two checkpoint files is actually a pretty good way to go. Okay, so even though, once in a while you might lose something, but, you shouldn't expect everything to be there, if the machine crashed right where you're typing something. All right, so these two files, checkpoint file 1 and 2, they are not part of the log structure, okay, but they are very crucial in terms of maintaining, be able to find all the inodes, in the current file system. All right, so using this particular approach, write can be really fast because you're going to do one long write, writing 1,000 sectors, including the inode map pieces at the end that are affected, okay, and then you go and update, and then you go make a backup, perform a checkpoint operation, and then you can continue to go from there. All right? Okay. All right. I guess this is a good point to break. So basically, we finished the first set of slides, talking about how to use 100% of the disk. Right, so now we sort of know how to make 100% of the read, you use 100% of the disk speed when reading and also when writing. Okay, next part of, let's go back here. Okay, we are right here. We finished the basics of file systems. Okay, the next 3 set of slides in chapter 6, right, we said we're going to finish this first after chapter 7, second after chapter 7, third after chapter 7. So we're basically done with chapter 6 at this point. Okay. Next week we have the midterm on Monday, and Wednesday we're going to talk about the very important, topic of chapter 7 because that really affects your kernel 3, and kernel 3 is very tricky. We're going to start talking about virtual memory, so get you ready for kernel 3. Okay. And again, kernel 2. It's pretty straightforward. You want to implement virtual file system. So you basically you implement all those system calls. The file system call. I guess everything has a do in front of it. So there's do open, do read, do write, do link, do dupe, I guess all the system calls that we talk about in chapter 1. Those are the ones that you have to implement in kernel 2. Okay. All right. So I'm going to see you guys on Monday in where do we go? SGM. Okay, let me go over there. It's going to be SGM 101, right? SGM is section 4B of this campus map. Okay, where is 4B? 4 is right here, B is right here. All right, so it's somewhere in this region, okay? All right. If you have questions, feel free to send me email about the midterm exam and also the lecture slides.
It's been CS 402 on Wednesday, July 2nd, 2014.